talking about moments of inertia. And in addition to moments of inertia, we will also get what we term as products of inertia. Now, so far we have not talked anything about dynamics, about how a body moves, or if forces are acting, couples are acting on a body, how does it move. But when we talk of a rigid body, then it turns out that there are certain quantities of interest which come out, which are related to a rigid body, and they are a couple of them would be these inertia, moments of inertia and products of inertia. So we'll do these, and it may look like why we are doing these, but the actual application of this will come in once we go to dynamics, and there we will see the role played by what we call the moments of inertia and products of inertia. So right now, if you find the discourse a bit too mathematical or too abstract, or maybe a bit too tedious just in terms of too many things to be done, it may be like that, because the physical motivation of this will come in only later. So now we define, and I can term this as an inertia matrix for any body. Typically we use these for a rigid body, but this could be used for a deformable body also. The only thing is, if we use it for a deformable body, then these quantities will change, but if we use it for a rigid body, then they will not change, because the way these definitions come. So let us have a look at these definitions. So let's consider a rigid body. So we have some body of arbitrary shape. This is a rigid body. Now what we do here is, we at some point O on the body, we fix the coordinate axis. So there is a point on the body on which we fix three axes x, y, z. Now if we fix them on the body, one thing you will realize is, as the body moves, the axis will also move with the body. And this particular distinction right now it does not matter, but later on when we talk of the dynamics of the body, it will become important, whether you are fixing your axis to some point on ground or on the body. Let us say we have fixed them on a point on the body. Now if I look at a small element of mass dm, which is located on the body. So this is an infinitesimal element which we do for all the things. We choose some infinitesimal element dm. Now this mass dm is located at a point whose coordinates are x, y, z. Okay, is that fine? So this is simple. This is how we do anyway. Any relation we derive, we choose some general point located at x, y, z, and then either that point is in infinitesimal in length, or in here we are talking of the mass, which is infinitesimal. Now what we do is, if I look at, or let me first remove the integral. if I look at this quantity, y square plus z square times dm. What does this represent? Dm is the mass. What is y square plus z square for this element of mass dm? It is the square of the distance from the x-axis. Is that clear? So that is what y square plus z square is. So this is square of distance from x-axis. So this I do it for dm, and now I add up all such quantities over the entire body. So I look at this mass dm, I do it, I look at the next one and look at the next one, and keep on doing this till I cover the entire body. So how will I represent that? That will be represented by an integral. So when I say integral, let me put it m, which means integrating over all masses. Now the mass could represent density times dV, so then it will become a volume integral, and so on. So I add up all these quantities, and this quantity is what I call as the moment of inertia of this body with respect to the axis at O about the x-axis. So now there are two things which are important when I talk of moment of inertia, or three things. One is I am talking of the axis. So it is about the x-axis. So about any axis I can define moment of inertia. It need not be x, y, z. It could be anything aligned, or it could be inclined to x, y, z also. All I have to do is choose that axis. I can call it x, and then I just look at the square of the distance of each of the mass from that axis, add it up, that gives me the moment of inertia. Is that fine? So this is how, this is what I call as moment of inertia of the body with respect to x-axis and somewhere hidden is also the fact that the origin is at O. Now I will need to, either I can put it as somewhere maybe on that superscript I can put O or whatever. So there will be some indication of that also needs to be there in my symbol. Right now I have not put anything because I was in it at O. And you will appreciate if O is fixed to some other point, then this quantity will change, because now it will be related to the previous one, but it will change. Is that fine? So this is how we define moment of inertia of any body. Of any body. Any body is different from anybody. Okay. So that is how this is done. Now, what is the physical significance of moment of inertia? As I said, we'll appreciate this more and more once we come to dynamics, but right now it would be sufficient to say, suppose if the body were rotating about the x-axis, then moment of inertia will tell me if it is to start rotating and it reaches an angular velocity omega, then the time taken by the body to reach angular velocity omega will be directly proportional to the moment of inertia of the body. And this right now I am stating without saying anything, and so it basically, moment of inertia will have to do with the angular motion of the body about the axis. It is some quantity which represents the inherent quantity present in this body, which either resists or causes the motion, rotational motion about that axis, and that is why the word inertia in the name. So this is called as moment of inertia. Is that fine? So I can do it for any axis. In particular, we can therefore define similar things for what will be integral x square plus z square. This will be Iy and integral and actually so I can define Iy and Iz like this, and also sometimes if it is a general axis I could call it Ik. This is equal to integral d square dm, where d is the distance of dm from the axis k, or we may also use what is called an initial notation x sub k. So to represent the axis, instead of, for example, instead of y and z, x, y, z, we sometimes call them as x1, x2, x3, and then when we say xi, xi represents one of the three axes. So that is why I have written it in this form. So this is how we got the moment of inertia. Yes.
What is axis represent a vector or a line?
Pardon?
Axis. What is axis represent?
Axis is representing, in general sense, you're right. It's a line with a direction. See, any line has a direction, and in this case, see what you're saying, a vector will become important if the direction of that vector is important. Here, for these considerations, it doesn't matter whether your x is facing this way or going inside the board. So therefore, we don't really use the term vector. We just represent a line.
Then what is need of origin?
You'll just see that. I'll tell you why. Well, one thing is the origin may be shifted.
If this is a line, then origin, how can origin shift?
No, I'm saying for the body. See, now you have defined moment of inertia of this body. Suppose I calculated about a point A, which is on the body, but not O. So the moment of inertia about that point A, again if I have three axes, it will be different from about point O.
But axis is passing through origin, not from A.
No, axis would be passed, then the origin will be A. That is what I'm saying. So the origin becomes important. So O is the origin. So I'm saying origin at O. In the other case, it will be origin at A, origin at B. So the origin itself could shift.
If we keep this x-axis same,
Yes.
then the moment would not change.
No, if we keep the x-axis, is that what you are saying? But y and z are also there. So if the axis is the same, that's right. See, his question is, if the axis is x-axis, then it doesn't matter where the origin is. But the origin becomes important when we look at Ix, Iy, Iz together. If I just look at Ix, origin may not be important. But it has to be on that x-axis itself. And as you will see, as we change points, there could be an axis which is parallel to this x-axis, but passing through some other point. And that is where we will do, what is it called? The parallel axis theorem. Okay. So this is what we term as the. Now, are there any properties of moment of inertia which directly follow from this, which are obvious? Well, one thing you directly see from this is this quantity has to be either greater than or equal to 0. It can never be negative, because it is always dm multiplied by square of something. So therefore, these moments of inertia, they are always greater than or equal to 0. Okay. Now, let me define 3 more quantities, or rather there will be 6 more quantities. If I look at, and I'll do this right now, we have x, y, z, d, this thing. Suppose I define integral of x times y times dm. Think of it just as a mathematical exercise as of now, because right now it will not, why will such a thing appear, where will it appear from, is not easy to see. This quantity integral xy times dm is what we will refer to as Ixy, and this we will call as product of inertia with respect to xy axis with origin at all. Okay, उसी पे तीन बनी थी ना, वो पे x, एक x थी, एक y थी ना, तो x कॉमा y है भाई. It is x comma y and there is a plural here. I didn't write x's, I wrote x's. So there are two. So that means one thing is very clear. For you to be able to define a product of inertia, we are talking of two mutually perpendicular axes. It can't be about a single axis. It has to be a quantity like product of inertia. So this has to be about two mutually perpendicular axes, x and y. So now similar to this I could have integral yz dm, and this I will call as integral iyz. So these three quantities x, y, yz and ixz, these will be termed as products of inertia. Now once again, as I said, the discourse gets just mathematical. What is the physical significance of products of inertia? And we will have to defer it to a later stage. The only this thing what I can tell you as of now is, suppose if product of inertia is not 0, let us say Ixy is not 0, and you are giving a couple to the body about x axis. So then what do you expect? The body will rotate about the x axis. You are giving a couple about x axis, but physically what we will show is, if Ixy is not equal to 0, then even a couple just about the x axis will also make the body rotate about the y axis also. So for example, if you give a rotation about the couple about the x axis on a body, you expect the body only to have omega x, omega about the x axis. But if this quantity is not 0, then not only will the body rotate about the x axis, it will also tend to rotate about the y axis in addition to the x axis. So this is the physical effect of these products of inertia, that they tend to make the body rotate about the other axis also, even though no couple may be applied to the body about that second axis. Now why don't we see this for most common bodies? When we rotate this, we only see rotation about that axis, we don't see the rotation about the second axis. So what common sense observation can you make out of this? That this quantity must be 0. And what we will learn, at least either by today or by the next lecture, is at least by inspection, can we locate when will these products of inertia be 0, or how do we find out these products of inertia? So that is what we will be finding out eventually. So these are three things called products of inertia. Now the products of inertia do they have to be positive or can they be negative? They can be because it is integral xy dm. You can place your xy anywhere on the body, and so therefore they can be either positive or negative or 0. Okay. Now, so now what you see is, again let me draw this cartoon again. There is some point O. So with respect to these coordinate axes which are now fixed at O, how many of these inertia terms have we defined? We have defined actually 9. It could be 9. What? Let's see these. So let me write them in a matrix form. We can define Ixx, or in fact actually this Ixx, I am writing it Ixx, actually we have called it Ix. But because I am writing in a matrix form, let me write it as Ixx. Then I have Ixy, Ixz, Iyx, so these quantities which I have defined, I can express them in a matrix form, where the diagonal terms, so now this matrix I can call it as the inertia matrix, yeah. And Ixx, Iyy, Izz, these are the diagonal terms, and these are same as Ix, Iy and Iz, and these are positive and these are referred to as the moments of inertia, and Ixy, Ixz, now, is there any property which you can think of this inertia matrix which comes just by the definition of the matrix? Symmetry. It's a symmetric matrix, because Ixy and Iyx are just integral xy dm or integral yx dm. They have to be the same. So therefore, by definition of this, you can see that this matrix okay. Now, have you had some course in linear algebra, or are you doing, or you have seen some linear algebra? So you must have seen a lot of properties of symmetric matrices. All those properties will apply to this. Do you remember the term eigenvalue? Have you talk of what is termed as the parallel axis theorem. Parallel axis theorem deals with a case that in case if we know either one term, I'll use inertia matrix. That means it can be used to every component of the matrix. It could be used to every xyz, ix, iy, iz. If I know the moment of inertia about point A, about the origin at point A, and I want to find the moment of inertia of the same body with the origin at point B. How are these two things related? And when we say parallel axis theorem, then what is assumed is, if I have x axis, y axis and z axis passing at A, and I make x, y, z at B, then these two set of axes are parallel to each other. That means the x axis at A and the x axis at B are parallel to each other. Well, I can, obviously somebody is doing it, nobody can stop me from making a set of axes at B where x, y and z are not parallel to the x, y, z at A. But when we talk of parallel axis theorem, x, y, z axis at the 2 points are always parallel. And what we will see is, in the parallel axis theorem, so this we will want to find for the inertia matrix. So now we will talk of a special point, the center of mass of the body, and the center of mass, let me physically try to locate it at a, our textbook uses a symbol G for center of mass, so I will use the symbol G. Okay. So let us say and following the book's notation, we have the axes which are passing through G, we call them x prime, y prime and z prime. Okay. And we have a general point A, the parallel set of axes passing through this point, well, they don't look very parallel, but we call them x, y, z. So and x prime is parallel to x, y prime is parallel to y, z prime is parallel to z. Okay. Coordinates of the point G, that is the center of mass, are x bar, y bar and z bar. They are the coordinates of point G. From which axis? Obviously from the axis at A, which we are calling x, y, z. So the point G has coordinates x bar, y bar, z bar. Now what we want to find out is the relation between, let us say Ix with the axis at A and the axis at G. Okay. So let us talk of Ix. This will be defined as integral of y square plus z square dm. Now y can be written as y bar plus y prime Is this obvious or not? Because y is the coordinate of the point from A. I can take this with respect to, first I go to G, and from G I go to A, to the point P. I am looking at a point P whose coordinates are x, y, z. So I first go to the point G, and from G I go to P. So what I am saying is the vector AP is equal to the vector AG plus GP. Okay, so here what I am using is the vector AP is equal to the vector AG plus GP, and I am looking at the components of this. Okay, so now all my formula, what I am trying to do is I am trying to relate Ix to I with the x's at the located at G. So all I have to do is in this y I will substitute y bar plus y prime, and in the z I will substitute z bar plus z prime. Let's do that. So this becomes equal to integral of y prime plus y bar square So I have just expanded each of these. There are 3 terms in the first here, there are 3 terms here, so totally I get 6 terms. Now how will I club them? I will take it as y bar square plus z bar square dm. That will be one clubbing I will make. The second clubbing I will make is y prime square plus z prime square dm. And the third clubbing which I will make will be the 2 terms with the 2's. So let's do that. So this I can write it as equal to integral of y bar square plus z bar square dm Now, in these integrals, is there anything which can be pulled out of the integral? What quantity can I pull out of the integral? The quantity which does not depend on point P. Point P is something which is moving. It has coordinates x, y, z, and that keep on changing. But anything which has nothing to do with point P, which is fixed, can be taken out. So, as you rightly said, y bar and z bar, they are not linked to point P. They are the same for all points on dm, so they can be pulled out. So this will become y bar square plus z bar square outside integral dm. Is that clear? What about here, y prime square plus z prime square dm? Can I pull this y prime and z prime out of the integral? No. Why? Because y prime and z prime are the coordinates of point P in the centroidal axis. So they will keep on changing. So this can't be pulled out. In the last 2 terms, what can be pulled out? Y bar can be pulled out and z bar can be pulled out. Is that fine? So let's do that at the next step in simplification. So this becomes equal to y bar square plus z bar square integral dm plus Is that fine? So now, how do I simplify this? What does this become? The total mass times y bar square plus z bar square. So the first term becomes m times what is the second term? Y bar square plus y prime square plus, it is Ix about the centroidal axis. So this I can write it as Ix, and I put a bar on this to represent this is Ix about an axis passing through G. What happens to the last two terms? What is integral y prime dm? Let us try to think, and I have got the right answer. Let us try to show this. Let me just make a small detour here. How do we how do we define the coordinate of the center of mass x bar? So x bar we define as m times x bar is equal to integral x dm. Similarly, m times y bar is equal to integral y dm. This is how you look at the center of mass. Now in case if my origin is at the center of mass itself, what will be this quantity? 0. And what will be this x? It will be x calculated from center of mass. So what this tells me is that if you fix yourself at center of mass, then x prime dm will be 0. Similarly, y prime dm will be 0 because now you are sitting on the center of mass itself. So therefore, so I am just giving a very physical argument, I am not giving a mathematical argument. If we sit at G, x bar, y bar are 0 and x, y's are nothing but, in our notation they are x prime, y prime. So this implies integral x prime dm is 0 and integral y prime dm is 0, etc. Does everybody see this argument? Okay. So therefore, following this argument, if I move up, these two terms are equal to 0, and what I get is moment of inertia about x axis at any general point will be equal to moment of inertia about x axis passing through center of mass plus mass of the body times y bar square plus z bar square, where y bar and z bar are the coordinates, or these are the location of the center of mass. So y bar, z bar are the y and z coordinates of G as seen from x. Okay. So this is what the parallel axis theorem is. Is that fine? Similar to this, we will be able to get things for y and z. Okay. So now, in this theorem, what do we see? What is the physical meaning of y bar square plus z bar square? the distance of the distance from the x-axis of the center of mass. So if we look at the center of mass in the new axis, what is the distance of that with respect to the x-axis, square of that. So if we are talking of the x-axis, then we look at the distance from the x-axis of this point, square of that, and that multiplied by the mass has to be added to the moment of inertia with respect to the center of mass. Sometimes you have a confusion. If you have a confusion, always keep in mind that the minimum moment of inertia is through center of mass. If you go away from center of mass, the moment of inertia has to increase. So that way you will remember where the plus sign comes. Okay. So this is how we work out the moment of inertia. So this is this term, let me just say, I'll write the physical meaning. Y bar square plus z bar square, this is the square of the distance between the x-axis at A and the x-axis at C, at G, sorry, not C. Sometimes we use G and sometimes we use C, so therefore the confusion. But this is, so you look at the two x-axes from the 2 points, the distance between these two axes, square of that is what has to be added, multiplied by the mass, of course. Okay. So this is the, similarly you will have for y-axis and for z-axis. We don't need to do it. Now we can derive a similar theorem for product of inertia. Okay, so let's do that. I'll not derive it now because then it will be quite straightforward. Let me just state that what you will also have is Ixy so this will be the parallel axis theorem for products of inertia. Okay. So we have a parallel axis theorem for. Now one very common mistake one can tend to make. I know the inertia term, let us say the moment of inertia at point A, and I want to find out the moment of inertia at B. I can't apply the formula directly from A to B. I have to go from A to G and from G to B. Calculation wise you may do it in one go, but notionally the formula relates only A to G and B to G, and then you eliminate G to get A to B, but you can't use the formula between A and B. So the formula has to have this thing as the centroidal axis, because only for the centroidal axis the last two terms became 0. For other axes they will not become 0. Integral y prime dm and integral x prime dm etc. they become 0 only for centroidal axis. So if you have to go from A to B, you have to go through G. So let's write this down also. So And the reason why this happens is that the formula is a non-linear one. If the formula was linear, if it was only x or only y, it has no squares, then it would have worked, you could have gone from A to B. But because it involves x square, y square or xy, then sum of squares is not equal to the square of sums. And that's why it doesn't work. So you have to basically, maybe in some cases it may work also, but then they are very special cases. When you, in some product of inertia formulas it may work, but that is because they happen to be 0, the other terms. Okay. Now, one more thing, maybe in product of inertia. So you see what you are talking of is one point centroidal axis and another point. Now in this formula you have m times x bar y bar. Suppose your point A and G are located in such a way that you are shifting only along one axis, let us say only along x. Then what will happen in the product of inertia formula? Nothing will change. Why? Because here you have at least two terms, x bar y bar z bar, x bar z bar. So if you are shifting only along one axis with respect to the center of mass, the product of inertias will not change. You have to have shift along two axes, along x and y, then x bar y bar will change. If you shift along x and z both, then x z will change. But if you shift only along x, then this will not change, but moments of inertia will still change. Products of inertia will not change unless you shift with respect to the origin, with respect to the center of mass, at least along two of the three axes. If you shift only along one, products of inertia will not change because of the product involved. Okay, so these are, of course, the best way of applying this formula is, see, till now you have done only planar sums. So wherever you applied this formula, you just looked at the physical problem and you calculated the distance between the two axes. But in three-dimensional problems, calculating the distance may not be so obvious. So best thing is, if you are shifting along all the three axes, you just use the formula blindly. That means you write what is x bar, y bar, z bar, you write what is I about these three axes, and write the I about the new axis. Because the distance, calculating the distance between the two axes, if you are shifting only along one axis is straightforward, but if you are shifting along two, then you have to take the distance of square of both the axes, and which may not be obvious if you are doing it by just looking at the picture. So then you should just use the formula. Okay. So this is moments of inertia. Now there is another type of, now we have seen a shift of origin. There is a second case. I have my axis x, y, z located at one point. Instead of shifting the origin, if I rotate about the axis, if I take x prime, y prime, z prime, x, y, z are my original axis, I keep the origin the same, but I rotate the old axis to a new position, keeping the origin the same. Then I will get new axes x prime, y prime, z prime, which are related to the old axis. And how do I write the relation between the old axis and new axis when I rotate the axis? I write them in terms of which quantity? There is something called direction cosines. The relation, when we rotate axis, we always write these relations between old axis and new axis in terms of direction cosines. What is a direction cosine? The cosine of the angle between the new x prime and the old x is termed as cosine of this angle is the direction cosine for x axis. Similarly, direction cosine of y axis will be the cosine of the angle between the new y axis and the old y axis, and so on. And I don't know if in maths you have been taught, probably this is what I was expecting when the matrix comes. The matrix formulations actually represent the general formulation if you were to rotate about the axis. What the matrix will tell you is it represents one configuration, and the matrix can be transformed by rotation, and each rotational this thing will tell you where the new axis will be for the new configuration. So, a generalized way of putting all these rotations is by putting them in a matrix form, and then the matrix operations will tell you how these things transform when you change the angles. So, we have a second thing which you can call, this was the parallel axis theorem. I don't think this any book calls it the rotation theorem. This is a name which I have given, and here what we see is if we have rotation of axis. So, for example, so now again this is my body, I am at any point A. This is now, this formula which we are deriving is not just only for, it is valid for any point. It does not have to do anything with center of mass. So, this could be, is this an indication of something? No. So, let us see. X, Y, Z, okay. I have an axis like this, and let me now talk of an axis which is passing through the same origin. So, it could be any line passing through this origin. I call this as KK. So, K is one axis which is passing through the same origin as which we have the X, Y, Z. Is this clear? So, what I have done so far, there is a point A, I have X, Y, Z axis at A, I know the inertia matrix at A. I have an axis KK, another line passing through the origin. I call that an axis. Okay. So, now we have, let me write this. So, at A we have X, Y, Z axis, and inertia matrix known with respect to the X, Y, Z axis at A, and let KK be an axis passing through A. Now, we say that the direction cosines of KK axis passing through A, B, lambda x, lambda y, lambda z, and sometimes we also use the symbols L, M, N. I think you must be more used to these symbols, and the textbook uses lambda x, lambda y, lambda z. So, that is why I am using this. So, now let us see what is this. Cosine of the angle between K and the x axis, this is equal to lambda x or L. This is the meaning what I am saying. There is this K axis. So, I look at the angle between the K axis and the x axis. I take the cosine of that, and that is what I term as lambda x or L. Similarly, cosine of the angle between K and y axis, this is termed as lambda y or m, and cosine of the angle between K axis and z axis, this is lambda z or n. Now, what I can show is what will be I about the K axis. I about the k axis will be, I look at the point P, wherever the point P is, I look at the perpendicular distance from of the point P from K, take the square of that distance, and that will give me, and add it up for all these, that will give me IKK or IK, I about K axis. And what I'll do is I'll just write the final form. When you write this in terms of all these other terms, what you get is this is equal to, I'll spare you of the derivation. I have done only one derivation, that is of the parallel axis theorem. Here similarly we have to just put everything in terms of the new axis and the old axis, and it's given in the book. What you get is this will be equal to, I'll write it in on the fresh page, IK is equal to lambda x square Ixx lambda y square Iyy lambda z square Izz plus, oh sorry, not plus, it's minus 2 So I get the formula for how, if I rotate, I get, if I know I about x, y, z axis, how can I find I about the k axis? Okay. Now you don't need to worry about remembering the formulas. पहली रो में बैठ के तो ये सब मत करो. You don't need to remember all these formulas. They can be basically, if in the exam they are needed, I will provide them to you. Okay. But this is how things get transformed in a rotational way. Now there's a term which we use, radius of gyration. Radius of gyration is just, you can think of it almost as a synonym of moment of inertia. If I have Iz, then I represent this as m times kz square, and kz is called so this radius of gyration is basically an engineer's, not shortcut, engineer's way of doing things. Instead of specifying moment of inertia for complex bodies, you will specify radius of gyration. So wherever the radius of gyration is given, then you know that you can calculate the moment of inertia directly. So either you use moment of inertia, find it, or you use radius of gyration. So basically this is just a way of listing things in a table. You will say radius of gyration of a circle, radius of gyration of a cylinder, and so on. Okay. One or two small things which I would like to do before we finally call it quit, and that is, so this is just a nominal terminology. Let's talk of something called principal axis, or first we will talk of a single axis called principal axis. Have you heard this term before? Principal axis. Matrix में कभी नहीं पढ़ा. You have not seen this. Maybe once I do this, you will probably realize. And a coordinate axis x, y, or z is said to be principal axis at A if products of inertia involving this axis are 0 at A. Now, with each axis, how many products of inertia do we associate? We associate with 2. So, for example, with the x axis I will have Ixy and Ixz. With y axis I will have Ixy and Iyz, and so on. So, with each axis we assign 2 inertias. And what we are saying is, if the product of inertia, so for example, if x axis passes through A and Ixy and Ixz are 0, then x is principal axis at A. So, principal axis is about making life simple, about making the product of inertia 0. If x axis passes through A, Ixy and Ixz will be 0, then we say that this is x axis is principal axis. Now, if all the 3 axes are principal axes, what will be the form of the inertia matrix? It will be just a diagonal matrix. All the off diagonal terms of the inertia matrix will be 0. So, that life will become simple. So, if x, y, z principal axis at A, then the inertia matrix is a diagonal matrix. It becomes Ixx, Iyy, Izz. The second thing which we see from this definition is, if suppose x axis if x axis is principal axis at A and y axis is also principal, then automatically z becomes a principal axis. Even though you may not get z from the argument, but if x and y are principal, automatically the third axis is principal. That is the second thing which we learn. Now, can we locate the principal axis by inspection? This is not given in your textbook, but is it possible to locate the principal axis just by, without doing any mathematical calculation? And one of the things which will help us will be symmetry. Suppose if we have a plane of symmetry in the body, then any axis which is perpendicular to the plane, that will be a principal axis. That is one conclusion we will get, that a plane of symmetry which is there, any axis perpendicular to that is automatically a principal axis. We do not have to even look at it, it will be, because what will happen is, the plane of symmetry cuts the body into 2 parts, a left part, let us say, and a right part. And when I have, if x axis is perpendicular to that, when I am calculating integral xy dm, then for each x I will have 2 y's, a left and the right, and if the axis is passing through the middle and we are placing there, the left part and right part will give me equal and opposite contributions. So, when I do integral xy dm, I will have integral, I can do it for the left part and the right part, for each x, yl and yr will cancel out. So, therefore, whenever there is a plane of symmetry in the body, perpendicular to that is a principal axis. So, if there are 2 planes of symmetry, what happens? Then the plane which is, or the line which is cutting the two planes, what you will have perpendicular to that, we will have one, perpendicular to the other one we have the one. So, in that plane which is the common to these two planes, all the axes will be principal axis, because at that intersection one of them will be a principal axis, the perpendicular to that will also be a principal axis. So therefore all the three will be, and again this I will show, I will probably this symmetry things I will show in the next class. But one thing we'll look at this, we'll move from here, but one thing we realize is, while I say that if there is a symmetry, perpendicular axis is a principal axis, the converse need not be true. That means symmetry is not a necessary condition. You will always have principal axis for any point, even if there is symmetry or no symmetry. How do we get that? Because I have a general matrix which has all the 9 components. Can I shift it to this form? I can always find a transformation which will shift the matrix to a diagonal one. And what will that be? That will be the eigenvalues and the eigenvectors of the matrix. I have a general 9 by 9 matrix. If I find the eigenvalues and the eigenvectors, basically they will tell me the orientation of that axis in this form. These will be the eigenvalues, and corresponding to each of these there will be an eigenvector that will give us the principal axis directions. So I'll again will look at this in the next class, but this is just some food for thought. For the next class I always like now this term, food for thought.